In the previous videos we've showed you how we can import a DXF file, and then we added a contour and a pattern for machining. So now we'll carry on and we'll take the drawing that we've created with those additional elements through into the machining software. So this is the file that we were working on previously. So what we need to do is save this drawing away. So we go File, Save As, choose the folder that you want to put it in and give the file a name. And then from the top menu we choose Machining, and we want to go into the milling module. So that transfers the drawing through to the machining software and gives us the contours and the patterns that we've created. So this is the milling software. So the first thing that is presented to us is the machine setup. So here we set up the machine type. Well, this is for a standard milling machine, and at this stage we might want to change our units, for instance. The program ID, we can set up the program identification. This could be a part name or a part number, and the NC program number is usually the number of the file that's at the top of the G code. So the next thing we need to look at is the tool change position. Pardon me. So the tool change position we can set up as X, Y, Z, and the same as the safety or the home position. The home position is where the machine will start from and where it'll end up. The tool change position may or may not be the same place. On many modern machine tools you don't need to drive the machine to a particular XY location for the tool changer to kick in. It can just be wherever the machine is at that time. So the XY tool change position and the home position can be at 0, but the Z value should not be at 0. 0, as far as part master is concerned, is the top of the job. So we need to set the tool change and this home position as being a value above there. So normally that should be quite a large value, but of course the actual value will depend on the travel that you've got on the machine. The clearance plane is a Z value which should be above the work surface and above and clear of any fixturing or work holding devices. So this is where the system will rapid between XY locations between features, so this should be clear of any obstructions. The feed change plane is where the system will change, plunging down in the Z axis, changing from rapid to a feed rate before it then goes into the job and machines the particular feature. On most modern controllers now, doing things like an M6T1 will switch off the coolant, stop the spindle, invoke the tool changer and so on. But on older machines you may have to manually intervene and have different M codes to switch the spindle off. If you need to do any of that, this is where you can use the check boxes to do that, but in most cases this is no longer needed. So we click OK. So the only information that has been passed through from that drawing is the contours that we created, one for the outside and one for that one circle there, and the pattern of holes which is for drilling. We can see that the datum position is the bottom right hand corner because that's where we set the datum when we were creating the contours. The screen layout, across the top of the screen we have the options for setting the view and setting the tool and running the job. Now some of these commands are greyed out because we haven't got any commands to simulate, therefore we can't press the simulate button. On the right hand side we see a status panel, and that will show us where the tool is, the current spindle speed, the feed rate and the cycle time. The main graphics area in the center is where we'll see the tool moving on the screen. On the left hand side we see the geometry definitions that we've got. So we have contour 0, contour 1 and pattern 0. The tooling definitions is empty for the time being because we haven't defined any tools, and also the program operations window is empty because we haven't created any program operations. So to do those things we need to use the bottom toolbar here. So the far left option is the setup, which is the one that was presented to us when we came into the CAM system. If we need to go back and change anything, we simply click that setup button, and then this is where we can change things like our tool change or our home position. To define tools, we use this icon here, and we're presented with a dialog box for setting up a tool. So we need to choose what type of tool we're going to be using. So in this case we'll use a simple end mill. The diameter of the tool, the lead not used for an end mill, the length is the length here, but this is just a visual thing and it won't be transferred through to the machine tool. You still set the tools on your machine exactly as you're doing them at the moment. The tool length, we could set that value so it looks more like the tool we're going to use. And this line here represents the maximum cutting depth. So we could use that value to control the number of passes that are used in the Z-axis. Tip radius, if we need to use a tip radius we can enter it there, but in most cases for a standard end mill that would be 0. When we use the term end mill we can use that for any type of standard milling cutter. Could be a slot drill or it could be an end mill, the same thing. The tool number, if you've got an automatic tool changer, this will be the tool number that it invokes, and if you need to put in a description of the tool then you can do that here. On some controllers pardon me, they use the tool description to invoke the tool, not the tool number. So if you have such a controller like a Siemens SimNumeric, then you need to set the description to match that which is in the controller. So well, that's just defined the tool. The next thing we'll do is we'll use that tool. So we invoke a tool change, M6. So we choose the tool that we want to use. There's only one tool that we can pick up, which is tool number 1. The length and radius offset registers are not generally used. Again, on older controllers you might have tool number 1 invoking offset register D21 for a radius value and H51 for the length offsets register. But in most cases just calling up the tool number will set those for you. The spindle speed, this is where you set it here, pretty much always going clockwise. And we've got two feed rates. The principal feed rate, in this case in X and Y, can either be expressed as feed per minute or feed per rev, and the Z-axis feed rate is what will happen when the tool plunges down in the Z-axis. If you want to switch on the coolant, this is where you do it. So that's selected that tool for use. Now on the right hand side the tool change position is shown to me because the machine is at this home position and the tool is drawn on the screen there at XY0. So now we need to produce a couple of machining operations, and what we'll do is we'll do a simple go round operation around the outside and then a simple drilling operation for those holes. So we use the go round command. So the first thing it needs us to set is the name of the contour that we want to machine. If there are multiple contours we can choose from the pull down list. If we don't know the names or can't remember the names, we simply use the select button here and point to the contour that we created in the CAD system. As I hover the mouse over there you'll notice that it's also showing me the direction that the contour was created in. Under Z planes, this is the information that's previously been set. we set the work surface to 0 and we set the depth of the contour to 15 when we created the contours. But if I want to change my mind, I can simply put in a different value here. For machining in the forward or reverse direction, and then the offset is applied after the direction is set. So if we wanted to go clockwise around there, that's the forward direction, and the offset is to the left. Finishing allowances, we can put things in here if we want to, but for the time being we'll leave those as 0. The approach and runoff are quite interesting. So the approach is how the system will move the tool to the beginning of the contour. If you can remember, we used this bottom line as our first line when we created the contour, so the approach movement will start from there. And the type of approach can be normal, arc, parallel or rectangle. We'll leave the defaults as they are, and the same for runoff. We will go into much deeper depth about all these options in subsequent videos. So that's showing me the tool going from the datum position there. The dotted red line is a rapid motion, the arc approach there, machines all the way around, and then the arc runoff. If we want to view the tool in different ways and the graphics in different ways, we use the toolbar at the top here. So if I want to see just the tool center line, and then I run the job, so that's just showing me that. If I click into the graphics area, and I can use the mouse to zoom in and out, so we can now see the arc approach movement onto that and the arc runoff. If we want to view the tool, we animate the tool and run the job. So that's moving the tool around there. If we view in the isometric view, and again we just zoom in and zoom out using the mouse wheel, and then we run the job. So the tool starts from the home position, rapids across in X and Y, rapids down to the feed change plane, which is 3 mm above the job, feeds down to the depth, applies the arc approach, machines all the way round, and then applies the arc runoff, and then retracts back to the clearance plane. So we can rerun that tool path and look at it in various views as we need to. This is the front view, so I can see that the tool is going down to the depth I specified. Whilst the tool is moving on the screen, the status panel on the right hand side shows me the tool position. So if I just go back into the ISO view and run that, and we look at the status panel, we can see the XYZ display being updated, and it's also calculating an estimated cycle time for us. So the cycle time is based on the X and Y feed rates value. We don't take into account the rapid feeds because we don't know how quickly a machine can go at rapid. So that machine's all the way around there. So in this case we'll leave that as it is and we'll continue with the drilling. So the first thing I need to do is to define the tool. So I go back to define the next tool, which this time will be a drill. Again, I give it the diameter. The lead is from the drill tip to the shoulder, and it's calculated on a standard 118 degree tip. The tool length, again, doesn't really matter, it's just for a visual thing for the tool on the screen. When the drilling takes place, the system will automatically add the lead value here onto the Z value that we give it, but there is a switch in the drilling dialog box which will switch that feature off, which I'll show you in a second. So that's defined the tool. Now we can invoke the tool changer. This time we're doing tool number 2, set the spindle speed and the feed rate that we want for that tool. If we want to switch the coolant on, that's where we do it. So that invokes the tool change. If you've got an automatic tool changer, then it will just change the tools for you and carry on the program. If you have a manual tool changer, then the machine will stop, the spindle will stop, and the coolant will be switched off, allowing you to change the tool manually. So to drill those holes, we use the drill command. The type of cycle that we've got is we've got a standard drill cycle, deep, peck, ream, bore and tap. The pecking cycles are the deep drill and the peck drill. A standard peck drill cycle keeps the tool within the hole as it's moving up and down. A deep drill cycle will withdraw the tool back to the feed change plane above the top of the job between each peck. So if you're doing deep holes where you need to clear the swarf between each cut, then that's the one to use. But in this case we'll just use a standard peck drill. The name of the pattern that we want to machine, well, there is only one pattern, and the Z-planes associated with that are the ones that were set when we created the pattern in the CAD system. Under the Options tab here, when it's travelling between the holes, it can traverse at the clearance plane, which is above any clamps or fixturings, as we set up in the setup dialog box. If we uncheck that, it skims across the top at 3 mm above the job. So depending if you've got any obstructions between the drill holes, will determine whether you need to keep this box checked or not. As I said earlier, if we want to ignore the tool's lead value when it's machining down to depth, then that's where we do it. To set up the number of pecks, we simply set the pecks there and click OK. So that's machining those holes as we wanted to. If I look at the front view and switch on the tool envelope, you'll be able to see then the different positions that the tool is taking when it's drilling those holes. So having defined those two operations, we can view the tool and view the graphics in various ways until we're happy with what it's doing. If I need to go and edit something or change something, I simply double click in the program operations window here and I can modify the values or the parameters that I've set. If we're happy with that, the last thing is to post-process. So this is where we create the G-code file, and we have a range of post-processors that come with the system. Let's just use a standard HAS controller. For that, it tells me that the post-processor has been compiled, so it'll do that once for each post-processor that you use. When it's finished that, another window is opened up at the bottom here, which is the G-code file, which we can send down to the machine tool. Okay, so that has shown us how we can transfer the geometry from the CAD system into machining and produce a simple